Okay, so today we are going to talk about Chapter 10, which is more bonding theory, but specifically we're going to talk about valence bond theory in this chapter, and then molecular orbital theory, which is a little more advanced than the Lewis theory that we previously discussed, but it explains more of the behavior that we see, which is a good thing. It turns out that when you start looking at the actual shape and the structure of different molecules, different elements, that their structure is going to determine the properties that they have. So the different shapes of the molecules are going to actually determine how they react with one another, the different functions that they have in the environment, sometimes the different functions that they have when they are, even in our bodies, okay? I think we've talked about the sodium and the potassium gates, the gated channels. That's an example of this, okay? So these are the three main things that the structure depends on. And the bonding theories are what allows us to predict the shapes the molecules are going to form once they start to bond to one another. Okay, our molecules are three-dimensional in space. We draw them on paper as 2D, but that is not what they actually look like. And the shapes of the molecules are going to look very similar to standard geometric figures. They're going to have specific angles associated with them around the central atom. And that's going to be like the optimal positioning to decrease the amount of repulsion between the electrons in a molecule. Okay, so when we looked at Lewis theory, which is a simpler version of bonding theory, we counted up the number of valence electrons and we placed the shared pairs of electrons between the two elements, right? So anything that was sharing, we would consider that a bond, and we would put it between the two elements. And any unshared valence electrons would be attached to a single nucleus, and that's how we represented the different electron groups in Lewis theory. Okay, so that allows us to determine what electrons are being shared and what electrons are singly associated with one particular element. Okay, now what's important about this is that our electron groups, which are what we're going to call those pairs of electrons, those bonding pairs and those non-bonding pairs, those are electron groups. So electron groups are going to naturally repel each other, right? Because that negativity doesn't want to be near more negativity. And the repulsion is going to dictate the shape of the molecule, right? So whenever we're trying to figure out what shape a molecule is going to form, the shape it's most likely going to form is going to be the shape that minimizes repulsion between electron groups. All right, so the electron groups are always going to try to get as far away from one another as possible. This is just the visualization of that. Okay, so if you have a central atom and then you have three elements that are attached to it, all right, these elements are going to space themselves out so that the electrons that make up their bond can be as far away from the next pair of bonding electrons as possible. Okay, that's the most stable form, when those electrons and the electron groups are as far apart from one another as possible. We count electron groups, like I said, as lone pairs of electrons. Okay, so every lone pair of electrons is one electron group. So this is an example of a molecule that has quite a few different, it's nitrite, so it's got a single bond, it's got a double bond, and it's got a lone pair on the central atom. Okay, now the central atom is where we're going to be counting electron groups from. Okay, so You know, we see that there's a whole bunch of lone pair electrons around oxygen, but because oxygen is a terminal atom in this case, it doesn't matter that it doesn't matter how many lone pairs are surrounding it. What determines the geometry is the central atom. So around the central atom, we have this one lone pair here. So that's one electron group. And any electron bond is also one electron group, okay? But it doesn't matter what type of bond it is. Whether it's a single bond, double bond, or a triple bond, that is still just one electron group. So around the nitrogen and the nitrite atom, we have one lone pair, we have one single bond, and we have one double bond. That's a total of 3 electron groups around the nitrogen. Now, as far as the geometry goes, we are going to look at a maximum of 6 bonding electron groups. Okay. These electron groups form 5 basic electron geometries that we have to know about. Okay. Electron geometries are perfect geometries. So they're going to represent these geometric figures that have all electron groups represented as bonds instead of lone pairs, and all of the bonds in them would be equivalent bonds. So you wouldn't have something that was a superpolar bond and something that was a nonpolar bond. And any molecules that have resonance in them, it doesn't matter which resonance form you use, the electron geometry will be the same regardless of the resonance structure that you pick. And if you need to see that for yourself, maybe think about getting a model kit to look at for some of these. Now, molecular geometry is slightly different than electron geometry. Molecular geometry is the actual shape of the molecule. And the shape of the molecule is different from the electron geometry when you have things like lone pairs involved, all right? Lone pairs affect the shape of the molecule. You also might have electron groups that are different sized, okay? Or not the electron groups, but they're going to be attached to things that are different sizes. Or you might have electron groups attached to molecules that have a very different electronegativity. So any of these things can affect the shape. But the big one that you have to watch out for here is the lone pairs. The lone pairs are going to significantly alter the shape of the molecule and make the electron geometry and the molecular geometry very, very different. So here's one case. We have a carbon, we have a double bond to an oxygen, and then we have 2 single bonds to these hydrogens, okay? Now, if there were no outside influences here, okay, if this was a perfect geometry, then carbon having 3 attachments, each of these bonds would be 120 degrees from one another, all right? However, because you have the different electronegativity of oxygen to hydrogen, that's not what happens, okay? You end up with more repulsion here, okay? So these bonds end up pushing away from one another, and then the hydrogen bonds end up closer together because they don't have as much negativity as the oxygen does. Okay, so they get squeezed in a little bit over here. Now, when you have lone pairs, wait, I should say one more thing about this. This represents the situation we were talking about here and here, these last 2 points. We have oxygen, which is a different size and a different electronegativity than the hydrogen, okay? So that's the example of those second 2 points. Here we're going to talk about the effect of the lone pairs. Now, lone pairs occupy a ton more space around the central atom than a bond does, okay? And this is because, first of all of the electron density is only on that central atom. It's not shared at all between any bonding groups, okay? And you have 2 electrons solely focused on the central atom that's going to be a huge cloud of negativity attached to that central atom. So when we're thinking about the different repulsive forces that are happening, you could have lone pairs around more than one lone pair around the central atom, and two lone pairs near each other would be the highest repulsive force because it has the most negativity, right? Now, if you have a lone pair next to a bonding pair, that will still be very repulsive, but it's not going to be as repulsive as two lone pairs. And then the least repulsive interaction out of the group of them are two bonding pairs near one another, right? And we have to think about how this affects the bond angles. So the more repulsion, the more distancing you're going to have from one another. So it's going to bend your bond angles more than if there was less repulsion. Okay? So you're going to start seeing a skewing of the bond angles. So you could see the difference here between the bonding electrons and the non-bonding electrons and how that would look. So now if you have two atoms and each of these are a nucleus, the negativity in this case is spread between the two of them. So this is what a bonding electron pair would look like, right? Now over here you have a nucleus and this is a lone pair represented. So you see how that big cloud of negativity is solely focused on this nucleus now. So if we had two electron pairs, imagine another electron pair trying to come in here next to it. It would be so negative, it would have to come to, it would have to get pushed to the other side of the nucleus just to get away from some of the repulsive forces that are taking place here. All right. Now, what ends up happening is with the 6 main electron groups that we're looking at, you end up forming these 5 basic geometric shapes. Okay. Now these are electron geometries. So these ones are going to be the perfect ones. All right. They only contain bonds as electron groups. There's no lone pairs in the shapes that I'm describing right now. Okay. These are the perfect shapes. As soon as we start introducing lone pairs, again, that has to do with molecular geometry instead. Okay. So these are 2 electron groups is linear, 3 electron groups is trigonal planar, so on and so on. All right. And we're going to run through each of these. So starting off with our 2 electron groups, that's our linear geometry. Linear means that each of your terminal atoms will be 180 degrees from the other terminal atom. All right, that's what makes a linear shape. So it forms a straight line. All right. Electron groups that have a linear electron geometry usually have a linear molecular geometry too, because there are no additional electron groups that you can have here. All right, so if you have electron geometry that's linear, then you have molecular geometry that's linear. And that bond angle is always going to be 180 degrees. All right. And this is kind of what this looks like as an actual, it's kind of supposed to be a more realistic representation of what you would be looking at there in terms of the negativity. All right. Now, if you have 3 electron groups, that's trigonal planar electron geometry. So 3 electron groups are going to have a more triangle position around your central atom, and in a perfect molecule, you'll have 120 degrees between the terminal atoms. All right? That's sort of what that looks like there in space. Okay, now what we have here is our first derivative of one of our perfect electron geometries. Okay, so a derivative is what happens if we remove one of our bonding groups and we replace it with a lone pair. Okay, that's what's happening here. We're going to replace one of the electron groups with a lone pair, And this is what it looks like now. Okay, so you have the central atom. It still has 1, 2, 3 bonding groups around it, but now it only has 2 bonding and 1 lone pair. So now the bond angle is going to be less than 120 degrees, excuse me. And that's because you have to imagine this lone pair is taking up a ton more space around the central atom than a bonding group would take up. So the angle between these 2 bonds is getting squished together and it's getting smaller. All right. Let's actually take a second to look at what this would look like in reality. I have a few models that we can look at. Okay, so here's our first 2 groups that we're looking at. This would represent our linear. Okay, you see it makes a straight line. This is our trigonal planar. Okay, now this is our perfect electron geometry. So everything's spaced out exactly 120 degrees from one another. Now, if I remove one of these electron groups, okay, and now let's say that, okay, so now this stick right here with no atom attached to it, now we're going to assume that that is a lone pair of electrons. All right, so now what happens is that because the lone pair of electrons takes up so much more negativity, these start bending towards each other. Okay, so you see that angle gets smaller and smaller because that lone pair needs so much more space. Our next electron group is a tetrahedral electron geometry. And this is when you have 4 electron groups surrounding that central atom. These bond angles are 109.5 degrees in a perfect electron geometry. Okay, so it doesn't matter where you measure terminal atom to terminal atom from, the angle will always be 109.5 degrees. So from here to here is 109.5. From here to here is 109.5, et cetera, et cetera. And this is what it looks like on paper. Okay, so on paper it looks like it's 90 degrees. Okay, but that's because that's 2-dimensional. Once you look at this in 3-dimensional space, you can see the true angles of the shape. It's called a tetrahedral geometry because if you connected the atoms and then you put like a face on them, you would end up with something that had 4 sides. That's where the tetra comes from. Okay, so this is a tetrahedron because it has a 4-sided pyramid. All right, and this is what this looks like in space. Now we have more than one derivative of the tetrahedral electron geometry because the more electron groups that we have, the more derivatives we can have. So for our trigonal planar electron group, we only had 1 derivative because there's only 3 electron groups. So now with 4 electron groups, we're going to have more than 1 derivative. So first, we're going to look at what happens when we replace 1 electron group with a lone pair. Okay, so now instead of having 4 bonding pairs, we're going to remove one of the bonding pairs and we're going to replace it with a lone pair. Well, now instead of a 109.5 angle between our terminal atoms, they're going to get squished in a little bit more to around 107. We just call it less than 109.5, okay? You do have to know all of the bond angles for the different molecular geometries. But once we get to the derivatives, as long as you know that the bond angle for this particular shape is less than 109.5, that is fine. Now, this particular molecular geometry is called trigonal pyramidal. Okay, so if you were asked to draw the Lewis structure out for ammonia and determine its shape, you would have to draw out the Lewis structure and say, well, it has 4 electron groups, 1, 2, 3, 4. It has 3 bonding groups. It has 1 lone pair. That means it has, you have to know both of these things, that it has a tetrahedral electron geometry and a trigonal pyramidal molecular geometry. All right, so you should be able to figure out the electron geometry and the molecular geometry based on the Lewis structure that you draw. The second derivative is called a bent molecular geometry. Now, I'm going to go back a couple of slides just because I don't think I mentioned this. This over here, this derivative of trigonal planar, this is also called a bent molecular geometry. Okay, so there's one bent geometry that is for the trigonal planar electron geometry group, and then there is one bent molecular geometry for the tetrahedral group. Okay, and in this case, we're removing 2 bonding groups and replacing it with 2 lone pairs. So our bond angle is even more deformed here. So it squishes into around a 104.5, which again is more specific than you need to know, but it's even more of a decrease from the 109.5 degree angle. Okay. So these are our 3 derivatives for our main perfect molecule, and then our 2 derivatives of the tetrahedral electron geometry. Okay, so everything's perfectly spaced out here. As soon as we remove 1 bonding group and replace it with a lone pair, which is not visualized here, but you have to know that it's there, that's going to cause these bond angles to shrink. And then when we replace it with 2 electron groups, the repulsion increases even more. So this angle between the terminal atoms shrinks even further. 5 electron groups is our next category, and that is the trigonal bipyramidal electron geometry. Okay, and that is because you have 2 pyramids that actually form base to base. Okay, so it's a bipyramid. It's trigonal because it's got the three points here, right? So that's the basis of the name for the trigonal bipyramidal geometry. And you're going to have 5 electron groups that make this up. Okay, so in a perfect electron geometry, you have 2 sets of angles here. You have what are called the equatorial molecules. So those are like the equator, right? So they're going to cut through the middle here. And all of the equatorial molecules are going to be 120 degrees from one another, right? And then you have what are called the axial molecules. And the axial molecules are going to be 90 degrees from the equatorial ones. Okay, and we're going to take a second to look at this one, I don't know, on video because it's a little harder to see. Okay, so this is the perfect trigonal bipyramidal, and maybe it's easier to see now. So you're looking straight down the axial line right now. So from here down to here. These 2 that I'm holding onto here, these are my axial atoms. Now, you see the angle between the equatorial, how it's 120 degrees. So that's a lot of space. That's more space than the angle. See if you can see it. See it this way, right? This 90 degrees between here. So it's 90 degrees between your axial and your equatorial. But when you're looking at the equatorials from one another, it's 120 degrees. Now that becomes important when we're talking about when we start to remove bonding pairs and replacing them with lone pairs. Because, where are you going to remove the bonding pair from? The axial or the equatorial? the lone pairs are going to want to go where they have more room. So when a lone pair comes to replace one of the bonding pairs in this model, it's only going to want to replace locations that are in the equatorial position, because the equatorial position has more room between other electron containing groups. Okay? So this is what the trigonal bipyramidal looks like in terms of a drawing. Okay? You have two pyramids face to face, two pyramids. All right? This is a visual representation of the angles. So there's your 90-degree difference, and this is the 120-degree difference. And that's what we were just looking at. Now, your derivatives of your trigonal bipyramidal geometry, like I said, they are never going to be on the axial position. Okay, you can only place lone pair electrons along the equatorial position, because the equatorial position is 120 degrees away from one another. Okay, if we put a lone pair in the axial position, it would only be 90 degrees from all of these other terminal atoms, and that is far too close for a lone pair. Okay, so now let's look at the different shapes. If we replace one equatorial electron with a lone pair, that molecular geometry is called a seesaw shape. Okay, and if you look at this, you can see why, right? Because it actually looks like, you know, the two seats on a seesaw. So your electron geometry is still trigonal bipyramidal, but your molecular geometry is seesaw. All of your bond angles are going to be less than ideal in both cases. All right, so less than 120 in the equatorial position, less than 90 degrees in the axial position. If we replace two of our equatorial electron groups, we're going to get what is called a T-shape. Okay, and again, we're replacing equatorial only. But now when we replace two of our equatorial atoms, what remains forms a pretty general T-shape. The angles are not a perfect 90 degrees, however. They're slightly less than 90 degrees because you do still have some extra repulsion in this general area, so it's going to be pushing down on these terminal atoms. So it's going to ruin that perfect 90-degree angle. Okay, and then our third derivative is a linear shape. Now in this case, all of our equatorial positions have been replaced by lone pairs. Okay, now in this case, our lone pairs are the only thing that's surrounding the equatorial position of our central atom. They get to space out perfectly, and they also get to exhibit equal amounts of repulsion onto our remaining terminal atoms in the axial position. What this ends up doing is giving us a perfect 180-degree bond angle between our terminal atoms. It makes this a linear molecular geometry. Okay, so that's when we have two bonding pairs left, but we have three non-bonding pairs, and those would all be around the equatorial position of our central atom. Okay, now I just want to run through these again, I don't know, in person. So we start with our trigonal bipyramidal shape, and now we're going to remove one of our bonding pairs, and we're going to assume now that this space here is taken up by a lone pair. Okay, so now we have two bonding, one lone pair, and this is where you get, sorry, I just had to push that back in. This is where you get the name seesaw, okay? Because you see what happens, like this kind of looks like it could be a seesaw. That's where that name comes from for the shape. If we removed another equatorial bonding pair. And now we have two lone pairs, right? One on each side there in the equatorial position still. This is your T shape. Now your T shape, again, it's not going to be perfect because you are still going to have some bending in this direction from all of the negativity from the lone pairs that are going to be up in this general area. Okay. And then the third derivative is when you have three lone pairs coming out of your equatorial positions and you only have two bonding pairs left, and you end up with a linear molecular geometry. And our final geometry involves 6 electron groups, and that is going to basically form 2 square base pyramids, base to base. All right, and that is called an octahedral geometry. All right, so 6 electron groups. It's called an octahedral geometry because if you did take 2 square pyramids and put them base to base, the shape that it forms is an octahedron, which has 8 bases. Right, that's where that name comes from. An octahedral geometry has every terminal atom exactly 90 degrees from every other terminal atom. Okay, all positions in an octahedral geometry are equivalent. All right, now we're going to start looking at the derivatives because obviously it can't stay as easy as everything is equal and 90 degrees from one another. So when we remove one electron group, one bonding pair, and replace it with a lone pair, what we end up is a square pyramidal molecular geometry. Okay, so our electron geometry is still octahedral, but now our molecular geometry is square pyramidal. And that's because the shape that it forms actually looks like a square pyramid, right? We're missing the bottom part of it. Now, because we have a lone pair replacing this position here, our bond angles are no longer going to be 90 degrees. They're not going to be perfect anymore. Now they're all going to be less than 90 degrees because there'll be extra repulsion that's coming in from this lone pair. When we remove two bonding electron groups and replace them with 2 lone pairs, we end up with a square planar molecular geometry. Okay, so our 2 lone pairs are going to be in positions that are as far from one another as possible. And that's going to leave our terminal atoms in the same plane as one another. Okay, so they're going to end up being in what's basically an equatorial position from one another. And our lone pairs will be in an axial position. And the lone pairs want to take this axial position because now they are able to be 180 degrees from one another. And the bond angles between each of the equatorial terminal atoms will be 90 degrees from one another. Okay, let us look real quick at what that looks like. There's my octahedral. Okay, so here's your standard octahedral shape. So you see how we have every position is equal to the other position. Everything is 90 degrees from one another. Okay, now if we remove one bonding pair and replace it with lone pair, it doesn't matter where you remove the bonding pair. Okay, wherever you remove it, what you end up with is a shape that looks like this. Okay, so now you end up with something that looks like a square pyramid. So if you connected all of these sides and then connected them up to the apex here, you end up with a square pyramid shape. Okay, but none of these angles are going to be perfect because there is going to be pushing from the lone pair that's on the base here. It's going to push all of these up a little bit. So none of your angles are going to be exactly 90 degrees from one another. All right. Now, if we remove a second bonding group and replace this with a lone pair as well, now you have repulsion on this end and you have repulsion on this end. Okay? What that does is keep all of your equatorial atoms in the same plane as one another. Okay? So every bond angle here will be 90 degrees. All the terminal atoms will be 90 degrees from one another. Okay, so let's take a minute to look at this question. You have a central atom in a 3-atom molecule that forms 2 double bonds and has no lone pairs. What is the electron geometry of the molecule? Okay, so you have a central atom, forms 2 double bonds and has no lone pairs. Okay, so that describes the first electron geometry that we discussed, the linear molecule, where you have 2 electron groups. Okay, if it has a central atom with 2 double bonds, each double bond counts as 1 electron group. So it has 2 electron groups. That is a linear electron geometry. What is the molecular geometry of the HCN molecule? The Lewis structure is this. Okay, this time we're looking at for the molecular geometry. We have a central atom here. It has 1 electron group here, and it has 1 electron group here. Okay, that again describes a linear geometry. Linear both electron geometry and molecular geometry. What is the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? So 3 bonding groups and 1 lone pair means that you're going to have a tetrahedral electron geometry. But what does that mean for your molecular geometry? When you remove one of those bonding pairs and you replace it with a lone pair, that describes your trigonal pyramidal molecular geometry. Okay, imagine that a molecule with 6 electron groups is confined to 2 dimensions and therefore has a hexagonal planar electron geometry. If 2 of the 6 groups are lone pairs, where are they located? Okay, so say that you had to have your geometry squished down into 2 dimensions. Okay, and you have 4 bonding groups and 2 lone pairs. Where would your lone pairs want to be? You have 3 choices here. So would your lone pairs want to be in positions 1 and 2? No, that's too close together. 1 and 3, it's better, but it's still too close together. 1 and 4, in this case, would be the preferable position because they would have enough distance from one another. 2 and 3 would also be fine because that would be 180 degrees from one another. Which statement is always true according to VSEPR theory? I'll give you a second to read that. You don't need me to read it out loud for you. Okay, now be careful with questions like this because we're trying to define this according to the valence electron theory that we're looking at right now. Okay, so it's not that all of the statements are false statements, but only one of them is true according to the theory that we're looking at right this second. Okay, and that's that the shape of the molecule is going to be determined by repulsions more than anything else. Okay, so if we want to predict the shape around the central atoms, we have to follow a little bit of a set of rules. They're not really rules, though. They're just guidelines for you. The first is that you're always going to draw the Lewis structure first, always. Okay, people like to jump right into doing the shapes of these without the Lewis structure. That is a really great way to forget about lone pairs that you didn't realize were there. And you need the lone pairs because that's the only way you can determine the electron groups around your central atom. All right, so you're going to draw the Lewis structure first, and then you're going to count out the number of electron groups around your central atom. After that, you're going to classify each electron group, either a bonding pair or a lone pair, and you're going to count how many of each one you have. And remember that multiple bonds only count as 1 electron group. And this next part you don't have to do, but I'm telling you about the notation that I'm going to be using in many of these slides. I will label my bonding pairs as X, and I'm going to label my lone pairs as E. That's a very standard way to do it. So for example, in this Lewis structure here, I have xenon. It has 1, 2, 3, 4, 5, 6 electron groups total. 4 of those electron groups are bonding groups. 2 of those electron groups are lone pairs. So I would call this molecule an AX4E2 molecule. All right. PCl5 has 5 bonding groups and 0 lone pairs. That's an AX5E0 molecule. So the A represents whatever the central atom is. The X represents the bonding groups, and the E represents the lone pairs. Okay? Now you're going to take that, and then you're going to bring it over to table 10.1, which you have to have memorized. And you're going to determine the shape and the bond angles of each of your drawings. Okay? So when you look at the chart, your X value corresponds to the bonding group. Your E value corresponds to the lone pair number. So if you have an AX3E0, that's a trigonal planar molecular geometry. If you have an AX2E1, that's trigonal planar bent molecular geometry. All right. So let's run through this. Determine the molecular geometry of the nitrate ion. So what's the first thing we want to do? And I would recommend pausing this at this point and trying it out yourself. But the first thing you want to do is draw the Lewis structure of the nitrate ion. Okay, so remember, we're going to draw the Lewis structure by counting up the valence electrons, then distributing the electrons, making sure everything has an octet. In this case, the nitrate ion has 3 resonance structures. You can pick any of the resonance structures to work with because they're all equivalent in this case. Once you have your Lewis structure, then you can figure out how many electron groups you have. We have 3 electron groups here, and they are all bonding groups. Okay, that means I have an AX3E0. So that's a trigonal planar electron geometry, and it is a trigonal planar wow, I just stuttered on that. Molecular geometry. All right. Our bond angles will be exactly 120 degrees. See, there's no difference in the size of these terminal atoms, and there's no difference in the electronegativity of the terminal atoms. So this would be a perfect 120 degree separation, one from another. Okay, let's predict the geometry and bond angles of PCl3. So step 1, we're going to draw out the Lewis structure for the molecule. PCl3 has 26 valence electrons, so it ends up with 4 electron groups around the central atom, 3 bonding groups, 1 lone pair. That means it is an AX3E1 molecule. When we take that to our table, an AX3E1, it has a tetrahedral electron geometry and a trigonal pyramidal molecular geometry. So our bond angles will be a little bit less than 109.5. Okay, let's do ICl4 minus. First, we're going to draw out the Lewis structure. Okay, the Lewis structure here, it's an expanded octet. So we're going to have 6 electron groups around the iodine in total. 4 of those will be bonding groups, 2 of them will be lone pairs. That means that my molecule will be an AX4E2 molecule. Okay, so now I'm going to go to my table, AX4E2. That's an octahedral electron geometry, and it describes a square planar shape. So all of my bond angles will be 90 degrees from one another. Now, we've been describing how to find the geometry around one central atom, but you can have molecules that are larger structures, and they have many interior atoms. So you can apply this method of finding the geometry to any interior atom in a molecule. Okay, so for example, here we have methanol. The carbon and the oxygen would both be considered interior atoms here because they have terminal atoms attached to them. So we can describe the molecular geometry around the carbon, and then we can separately describe the molecular geometry around the oxygen. So if we draw out this Lewis structure, we would see that the carbon has 4 electron groups, and all 4 of them are bonding groups. This describes a tetrahedral molecular geometry. The oxygen, on the other hand, has 4 electron groups, but 2 of them are bonding groups, and they have 2 lone pairs up here. Okay, so an AX2E2 molecule has a bent molecular geometry. Okay, we have a bigger molecule here. This is glycine. So it has 1, 2, 3, 4 central or interior atoms, and we can treat each interior atom as its own central atom, and we can describe each geometry individually. Okay, so the nitrogen over here is AX3E1. That's going to be trigonal pyramidal. The first carbon is AX4E0. That's a tetrahedral molecular geometry. Carbon 2 is AX3E0. That's a trigonal planar molecular geometry. And oxygen is AX2E2. That is a bent molecular geometry. And there is no overall molecular geometry for the molecule. The molecular geometry has to be described per interior atom. Okay, so this is an example. We were physically describing the geometry or the angles at each point in this molecule. Okay, so let's take a second here. What's the molecular geometry around nitrogen in CH3 and H2? To answer that, you need to draw out the skeleton structure, do the Lewis structure of it, count up the bonding groups and the lone pairs. Okay? Take a minute and actually do it. Don't just wait for me. Okay, and that is a trigonal pyramidal shape around the nitrogen. And see how it's specified here. It said, what's the molecular geometry about nitrogen? Okay, it didn't say around this whole molecule. It said, tell me the molecular geometry of nitrogen here. So how do we represent 3D shapes on paper? Okay, you see what happens in the textbook all the time. We use straight lines as often as possible. But the problem with that is that we don't actually see what the molecule would look like. Okay, so we can represent the molecules as 3D forms by using solid wedges and what are called hatched wedges in our drawings of the molecules. All right, so to do that, we're going to put as many atoms as possible in the same plane as one another. And all of those atoms would be drawn with a straight line. Then any of the atoms that are in front of the plane or that are closer to us, for example, we would have a solid wedge representing those bonds. For any atom that was behind the plane, the straight line plane that these atoms made, those bonds would be drawn with a hatched wedge. Okay, so we're going to look at an example. We'll look at an example of one of these on, okay, so focus here on the NH3 that they drew over here and the CH4 that they drew over here, because I'll show you these both in 3D space. In the nitrogen, only one of the hydrogens could be in one plane. More than one hydrogen wouldn't be in the same plane with another hydrogen, which means that one hydrogen would be further behind this one, and one hydrogen would be in front of this one. So the one that's in front gets a solid wedge, the one that's behind gets a hatch wedge. In the tetrahedral shape, we're able to put two of the hydrogens in the same plane as one another. And then we'll have one hydrogen sticking out front and one hydrogen sticking out back, right? So let me just bring those molecules up real quick. Okay, so imagine that this here is your straight line, okay? This is your in plane, in the same plane as a piece of paper bond, all right? Now, your hatched wedge represents this molecule back here that's behind your in plane bond. The solid wedge represents the bond that's out in front of your in plane bond. Okay, for a tetrahedral, we're able to put two atoms. So these two atoms where my fingers are right here, these two can be in the same plane. That means that if you line them up with like an index card or something, the index card or the piece of paper would hit both of these atoms. Okay, so these two would represent your two straight lines in this drawing, right? This bond that's out back of your straight line, let me try to keep that in line for your viewing right now. So this one that I'm tapping right here, that's your hatched wedge because that's behind. Well, to me, it's behind. I don't know what it looks like to you guys. And this one up here, this is in front of the plane. So this is your solid wedge. Okay, and that's what's represented down here in this picture. Okay, the next thing we need to discuss is the polarity of the different molecules that we are forming here. All right, for a molecule to be polar, it needs to meet two conditions. It's going to have polar bonds, and it's going to have an unsymmetrical shape. Now we're going to determine whether or not it has polar bonds based on the electronegativity differences of the atoms making up the bond. We can use the bond dipole moments that we already looked at. And we want to know whether something is polar or nonpolar because it actually affects the behavior of the molecules. It affects things like boiling points, it affects things like solubilities. You may have heard the term like dissolves like before. Well, that's because polar molecules will tend to dissolve other polar molecules, where polar molecules will not dissolve nonpolar molecules, and vice versa. Okay, and non-bonding pairs are going to affect the molecular polarity because of their strong negative influence. So we have to keep those in mind when we're determining the polarity of the molecules that we're looking at. Okay, so this is an example of a polar bond. You have hydrogen on one end, chlorine on the other end. Chlorine is far more electronegative than the hydrogen. So the electrons are going to travel towards the chlorine. When that happens, the hydrogen ends up with a partial positive charge. It's not fully positive. It's just that we call it the electron density of the hydrogen has been decreased. All right, so there's many fewer electrons in this area of the molecule. Most of them have migrated to this area of the molecule. So the area near the chlorine has a very high electron density. The area near the hydrogen has a low electron density. So a slight positive charge ends up hanging out near the hydrogen, and a negative charge ends up hanging out near the chlorine here. So in this case, the bond is polar and the molecule is polar. Okay, now over here in this next example, we have a carbon with two oxygens attached. What that means is that we have two different situations here, because we have to look at the bonds first of all. So the carbon-oxygen bond, is that a polar bond? If you look at the electronegativity difference between carbon and oxygen, we see that oxygen is much more electronegative than carbon. So we're going to have a very high electron density near both oxygens and a very small electron density, low electron density near the carbon. Okay, and we can draw our dipole moments that way as well. But the molecule itself, is that polar? That's what we have to consider. Okay, now what happens if we have a dipole moment going in this direction and an exactly equal dipole moment going in the opposite direction? Well, these two things cancel one another out. There is no negative end and positive end of this molecule because you have these oxygens that are both equally pulling on the electrons that are present in the molecule. And the electrons don't end up clustered in any one particular area. Okay, so even though the OC bond in both cases, in both bonds here, they're both polar bonds, but overall our molecule is not a polar molecule here because the polar bonds offset one another exactly. Now in this case we have a water molecule. So we have the oxygen bonded to two hydrogens, and both of these bonds are polar bonds. The hydrogen has the low electron density, the oxygen has the high electron density. But what we also have here is this big area that's not represented in our 3D structure, but it is represented over here. And this is the area here where we have our lone pairs of electrons on the oxygen molecule. All right, so we have an incredible amount of negativity that's centered on the oxygen here. And we have these two hydrogens that are both exhibiting a partial positive charge. Because we have a net charge within this molecule, excuse me, we have a negative end here and we have a positive end, well, two little positive tails almost. This molecule is polar, okay? These bonds do not cancel each other out the way that our previous example did because of the geometry of the molecules. This CO2 molecule is linear, okay? There are no lone pairs involved. There's no extra electrons anywhere to offset the canceling of the two polar bonds from one another. In the water molecule, you do not have a linear geometry, you have a bent geometry. Because you have a bent geometry, your dipoles cannot cancel one another out. They end up resulting in a dipole in this general direction towards that set of electron lone pairs that are up here. So we have a highly negative space up here, and we have positive areas by the hydrogens. So to figure out if you have a polar molecule, you want to go through the same process every time, and you'll be able to sort it out for yourself. The first thing you want to do is draw the Lewis structure. We always want to draw the Lewis structure first in this chapter, okay? From there, you're going to determine the molecular geometry, okay? After that, you're going to look at your structure and you're going to look at every bond in that structure and decide if you have polar bonds or non-polar bonds. If there are no polar bonds anywhere, then the molecule is non-polar anyway. But if we have polar bonds, you have to kind of draw a vector. It doesn't have to be an exact vector, but you should draw a vector. And you should point towards the more electronegative atom on each bond. Okay, the length of the vector that you draw should represent the electronegativity difference between those bonding atoms. So if you have a big electronegativity difference, you should be drawing a longer vector. Then you're going to decide whether you have a polar molecule or not by summing the vectors together and seeing if you have a net dipole or if you have a zero vector. Okay, if you sum up your vectors and you get a 0, then you have a nonpolar molecule. If you sum up your vectors and you get a net vector, then you have a polar molecule. And let's run through the example of how we do some vector addition here. Okay, so for example, if you have two vectors that you're drawing and they're both in the same direction, they're additive. So two vectors in the same direction end up with one longer vector, excuse me, in the end. If you have two vectors in the opposite direction, but one is smaller than the other, you will end up with a net vector in the direction of the larger number. If you have two vectors in opposite directions and they are exactly opposite in, if they're equal in size but opposite in direction, those vectors will exactly cancel out and you will have a net vector of 0. So in this case, you would have a nonpolar molecule. This is what happened in our carbon dioxide example. We had two vectors, they were exactly the same size in exactly opposite directions. So the net vector between the carbon dioxide oxygens was 0. Now, all of our vectors are not linear like that, so we have to start looking at the different shapes. And this is why when you have things like a bent geometry, you end up with a net vector. So something, I mean, it's not exact size-wise, but something like this could represent that H2O that we're looking at, okay? And again, it's not perfect because these aren't drawn to be H2O, but if you're summing up angled vectors like this, then the sum of A and the sum of B is going to be a vector that represents both of them. Notice that the bigger contribution was from B, so the direction of the vector is a little bit closer to what we had over here. But the vector is longer because they're both still going in that same direction. Okay, if we're summing up vector A and vector B here, again, the summary, I mean, you see how it's a little bit closer. If we're summing up multiple vectors, we're going to do it piecemeal. Okay, so start by summing up A and B. You'll get a vector from those two. And then to finish, you'll end up doing your vector from your first addition with your remaining vector to get your final vector. Okay, or in this case, if you have vector A and B, that's your vector from that addition. Sorry. Now, if we're going to sum up vector C with our first vector addition, you'll see again we have a cancellation of vectors in this case. All right, so this is kind of a translation of what some of that will look like. If you have linear geometry and you have two terminal atoms that are the same electronegativity, you will have nonpolar. This chart right here is assuming that you have things that are the same electronegativity, okay? Because you can have something that's linear, but if you have two things that are very different in electronegativity on each side, in each terminal atom position, you would still have a polar molecule. So these are based on the fact that you're going to have similar atoms in your terminal position. Okay, so you see something with a bent geometry here, that would be polar because you have a vector, a net vector at the end. For trigonal, planar, and tetrahedral, your vectors would cancel out in these cases. If you have a trigonal pyramidal, your vectors would not cancel out in this case. Okay, so let's determine if NH3 is polar. The first thing you want to do is draw out the Lewis structure and figure out the molecular geometry of the molecule. Okay, so you draw it out. It's AX3E1. The molecular geometry is trigonal pyramidal. Trigonal pyramidal we saw on the chart from before, the vectors are not going to cancel out here. So we have our three vectors that we're going to draw, okay, or our three dipoles that we're going to draw. The arrow is going to face towards the nitrogen because it's more electronegative. Each of these bonds is a polar bond. Now, when we're trying to sum up these vectors, we'll see that the sum of the vector is, it's this one here that's dashed. Nothing cancels out here. This molecule is a polar molecule. Okay, now molecular polarity is going to affect solubility, like we said, and specifically it's going to affect solubility in water. okay? Because water is a polar molecule. So it is going to be able to dissolve other polar molecules. So things like ionic compounds dissolve in water. Also molecules that have, you know, if you can have a molecular compound that still has a good electronegativity difference, that can dissolve in water as well. Okay. This is just an example of what happens when you have something that is nonpolar, like oil, trying to mix with something like water that is polar. Instead of mixing, you get a layered effect. But we are going to, we're going to talk about all of this in more detail. But we're going to pause here for now, and we'll do our next bonding model in a separate lecture.